middle of the 19th century, before modern chemistry was established, a number of scientists experimenting with materials came to understand that matter was made up of different elements. They found that some elements were very similar, while others were radically different. What they could not understand was why these differences existed. Solving this mystery led to the development of the periodic table of the elements, which remains the major analytical tool of chemistry. Ancient metalworkers were perhaps the first to learn about the elements. Gold, silver, copper, and iron were forged in foundries as long ago as ancient times. By 1800, some 30 elements were known, and over the next 100 years, over 60 elements had been identified. As they studied these elements, scientists looked for patterns and how the different elements related together. In 1869, a Russian chemist, Dmitry Mendeleev, published this table of all the known elements. It is the forerunner of the periodic table we use today, and one of the most brilliant insights of science. Mendeleev's table was based on the increasing atomic mass of the elements. As he arranged the elements in his table, he found that some had similar properties. Those he arranged in vertical columns in his table. He also recognized that there were gaps in the patterns of the elements, and predicted that there were undiscovered elements that must fill those gaps. Later, new elements were discovered that fit his predictions. Today, we do not list the elements in the periodic table by their atomic mass. We list them by atomic number. The number of protons in the nucleus of the atom determines the atomic number of an element. The person who saw the importance of atomic number was a young English scientist by the name of Henry Moseley. He was a student of Ernest Rutherford, who had discovered the nucleus and gave a preliminary explanation of the atomic structure. Moseley understood that the significant difference between the elements was their number of protons. Once the number of protons is known, it is possible to determine the number of electrons in a neutral atom. It was not that Mendeleev was wrong in the way that he listed the elements. The atomic mass of elements increases as the number of protons in the nucleus increases, but atomic number tells us more about the element. The periodic law is the basis of the periodic table. It states, when elements are arranged in order of increasing atomic number, their physical and chemical properties show a periodic pattern. As we will see, the pattern of the table is tied to the very structure of the atom itself. That is what makes it such a useful tool. The periodic table is a type of map of all the elements. The position of the element on the table explains the structure of the atom and helps us understand how it will react with the other elements. The elements are organized from atomic number 1, hydrogen, to atomic number 114, unquadium. Actually, there are only 92 elements that are found naturally in the universe. Uranium is atomic number 92. Beyond uranium are the transuranium elements, which have only been created in laboratories. The elements are organized in horizontal rows called periods. The numbers of the periods are printed along the side. They are called the principal quantum numbers, or simply N. In period 1, there are only 2 elements, hydrogen on the extreme left and helium on the extreme right-hand side of the table. Periods 2 and 3 each have 8 elements. Periods 4 and 5 have 18 elements. Period 6 has 32, and period 7 goes from element 87 to 114 on this table. Where are the extra elements in periods 6 and 7? They are printed below for convenience, because that is the only way they can be fitted on a page. Not only is the position of the element in the period significant, but so is its position on the vertical column. These columns are called groups. Their numbers are listed along the top of the table. Elements in each of these groups have similar characteristics, and because of this, they have been given names. The elements in Group 1, for example, are called the alkali metals, and Group 18 are called the noble gases. The size, or radius, of atoms is an important factor in their bonding. The radius of elements decreases from left to right across each period of the periodic table. The numbers of electrons increase across the period from left to right, but there is also an increase in the nuclear charge due to the additional protons in the nucleus, which hold the electrons more tightly to the nucleus. The radius of elements also increases moving down the groups of elements. This is because there are more electrons, protons, and neutrons in the atoms. There is one element that is unique. It is hydrogen, atomic number 1, the most prevalent element in the universe. Hydrogen is listed in Group 1, but it is separated a little from the others. It has many of the characteristics of the other elements in Group 1, the alkali metals, but it is a gas and definitely not a metal. Every element has its own square in the periodic table, and within that square is contained the vital information of the element. This is the square of nitrogen. Its atomic number of 7 is written at the top. We immediately know that there are 7 protons in the nucleus of the atom, and when it is electrically neutral, the element has 7 electrons. Every element has a symbol that is used by chemists around the world. Some periodic tables, like this one, have the name of the elements, but many do not. Nitrogen's symbol is N, and uranium's is U, but not all of the symbols are that easy to remember. Gold, for example, is Au, which comes from the Latin word for gold, aurum. Some of the more rare elements are named after countries where they were discovered, or scientists. Chemical formulas are always written using the letter symbols, so it is helpful to remember some of the most common ones. The atomic mass of the element is the number written immediately below the symbol and name of the element. Nitrogen, for example, has an atomic mass of 14.0067 AMU. AMU stands for Atomic Mass Unit. Chemists often need to know the atomic mass of an element in order to accurately measure the quantity of substances. The atomic mass of elements almost always increases as the atomic number increases. The reason is that as the atomic number increases, there are more protons, neutrons, and electrons in the atom. Each proton or neutron equals about 1 AMU. Electrons have much smaller mass. As a result, the higher the atomic number, the greater the mass of the element. The last number at the bottom of each square describes the electron configuration of the element. The nuclei of atoms are relatively stable, but the electrons move about the nucleus and can move from atom to atom. When atoms react with other atoms, the electrons often interact so that 2 or more atoms become molecules, or they lose or gain 1 or more electrons. In either case, it is only the outermost electrons of the atoms, called the valence electrons, that are involved in bonding, and they are responsible for the chemical properties of the element. Each energy level can only take a limited number of electrons. The first energy level can take 2 electrons. The second and third can each take 8. The fourth and fifth can take 18, and the sixth can take 32. Notice anything? The number of electrons that can be accommodated in the energy levels is the same as the number of elements in the periods of the periodic table. The table reflects the structure of the atoms of elements. This is why the table is so useful. The first energy level can only take 2 electrons, and the first row of the periodic table has only 2 elements, hydrogen and helium. Hydrogen only has 1 electron, but the energy level can take 2 electrons. As a result, hydrogen is a relatively unstable element and often interacts with other elements. Helium has 2 electrons, and the first energy level can accommodate 2 electrons. As a result, helium is very stable and rarely interacts with other elements. In fact, helium is one of the noble gases that are on the right-hand side of the periodic table. The second energy level can accommodate 8 electrons, and there are 8 elements in the second period of the periodic table. Lithium has only 1 valence electron. Beryllium has 2. And so on until we get to neon, which has 8 valence electrons. The valence energy level of neon is full. Neon, like helium, is one of the noble gases. Elements do not interact in a random way. Each atom attempts to interact with other atoms so that the electron configuration of its outer valence energy level is full. It does this by borrowing, lending, or sharing electrons. This is known as the octet rule. As a general rule, the elements on the left-hand side of the periodic table are termed electropositive because they tend to easily lose their outer valence electrons, while those on the right-hand side of the table are electronegative, tending to attract electrons so they can fill their outer energy level. The noble gases are very stable elements because their valence energy level is full of electrons. Chemists can tell almost at a glance how an element will interact with other elements simply by looking at the location of the element on the periodic table. The last line in the square of each element on the periodic table is the precise description of the electron configuration of the element. These letter symbols refer to the electron orbitals, specially shaped regions where we might find electrons moving around the nucleus. Chemists are mainly concerned with the orbitals of the valence electrons because they determine how atoms bond together and the chemical behavior of the element. There are 4 important orbital shapes: S, P, D, and F. The s orbital can take a maximum of 2 electrons. The p orbitals can take up to 6 electrons. The d orbitals can take up to 10, and the f orbitals can hold a maximum of 14 electrons. There is a direct connection between how many electrons it takes to completely fill the orbitals at each energy level and the number of elements in that period of the table. Let's look at some examples of how the electron configurations of atoms are written. Hydrogen has only 1 electron in an S-shaped orbital. It is written 1s1. Helium has 2 electrons in an s orbital. It is written 1s2. This is saying in the first energy level, the S-shaped orbital is filled to capacity with 2 electrons. Lithium has atomic number 3 and is in the next period of the table. But look how its electron configuration is written. This is a shorthand that chemists have developed. He says that the electrons in the inner energy level are exactly like the electron configuration of helium. 2s1 is a description of the valence electrons. It is saying that in the second energy level, the S-shaped orbital is half filled with 1 electron. Reading electron configurations takes some practice. Let's read one more. Gold. The inner energy levels have the same configuration as the noble gas xenon, whose symbol is Xe. The valence electrons are the following: 14 electrons in the 4th energy level in f orbitals, 10 electrons in the 5th energy level in d orbitals, and 1 electron in an s orbital in the 6th energy level. It was only when chemists understood the electron configurations of elements that they could understand how atoms interact to make the millions of substances that we find in the universe. The electron configurations determine the chemical properties of elements, but they also provide a way of dividing the table into 4 blocks of elements with similar properties. Each of the blocks is named for the shapes of the orbitals of the valence electrons. The s block is made up of elements whose valence electrons are in s orbitals only. They are the elements in the first 2 groups on the left-hand side of the table. Group 1 are called the alkali metals, and Group 2 are called the alkaline earth metals. They are soft metals like sodium, potassium, and calcium that react readily in air and water. The s block is only 2 elements wide because s orbitals can only take 2 electrons. The d block elements occupy the middle of the table. These elements are called transition metals. They are strong metals such as titanium, chromium, gold, and iron that make useful building materials. The d block is 10 elements wide because d-shaped orbitals can accommodate 10 electrons. The f block elements are placed below the main body of the periodic table. The 2 periods are 14 elements wide because the f-shaped orbitals can hold 14 electrons. These elements are rarely found and become increasingly unstable the higher the atomic number. The most familiar is uranium, element 92, which is used as fuel in nuclear reactors and atomic bombs. The p block elements are on the right-hand side of the periodic table. These are some of the most common and important elements and include carbon, iodine, oxygen, nitrogen, and sulfur. The p block is 6 elements wide because the p-shaped orbitals can accommodate 6 electrons. Included in the p block are the noble gases at the right-hand side of the table. Because their valence energy levels are full of electrons, the noble gases rarely interact with other elements. Chemists sometimes talk about the elegance of the periodic table, and the reason they see elegance is because the table reflects perfectly the structure of atoms. It remains the most important organizing principle of chemists because it helps us understand the atomic structure of the elements and their chemical reactions. The periodic table remains a major analytical tool of modern chemistry. True or false? An element is determined by the number of in its nucleus. The atomic mass of all elements is the same. True or false? The periodic law states when elements are arranged in order of increasing atomic number, their physical and chemical properties show a periodic pattern. True or false? Transuranium elements are found in small quantities in remote planets. True or false? The horizontal rows of the periodic table are called. The vertical columns of the periodic table are called. Electron configurations determine the chemical properties of elements. True or false? The electrons in the outermost energy level are called the electrons. The p block elements on the right-hand side of the periodic table are 8 elements wide. True or false?